Hello and welcome to a lecture on transducer power gain. I'm Steve Ellingson. Here's an overview of this lecture. This lecture is about gain. First, note that there is no one definition of RF gain for a two-port. There are many definitions. Gain can be defined in a number of ways, and these different ways are all useful and all give different values. Now we've already encountered one, which is the intrinsic forward gain. We can also have the transducer power gain, which we're about to talk about. There's operating gain and available gain. So there's at least four different types of gain, or four different definitions of gain that will become important. But the one we want to talk about in this lecture is of particular importance for RF design, and that again is the transducer power gain, which we call variously either the TPG, that is the acronym, or sometimes abbreviated G sub T. G sub T. Now, to talk about TPG, we're going to have to introduce some other concepts. One of these is going to be available power, P sub A. We'll also have to talk about the power delivered to a load, P sub L, presumably something you already know about, but we'll refresh your memory. TPG in terms of two-port parameters, and that's where we actually define things and show how it works. I'll give you a couple examples to demonstrate the concept with some numbers. And then we'll look ahead. We'll foreshadow this concept of stability of two ports, which will be a topic of a future lecture. Okay, the embedded gain of a two-port. In the previous lecture, we defined the forward gain, and specifically the intrinsic forward gain of a two-port as the magnitude of the S parameter S21, magnitude squared. So you take S21, you take its magnitude, because in general it's complex, you square it, and that's what we call the intrinsic forward gain. Now, forward gain is an intrinsic property of a two-port in the sense that it only has meaning for the case where the input and output terminating the two-port are equal to the reference impedance, which we've been calling Z0. So in other words, if the terminating impedances at the input and output are Z0, then the intrinsic forward gain is in fact the most relevant gain. It's the actual gain in some sense. Now, often, in fact frequently, normally in RF engineering, we may not want that type of matching. In fact, that is the essence of amplifier design. We achieve different amplifier characteristics by selectively mismatching the input and output. So we need to define gain in a way that allows us to figure out what's happening when the input and output are mismatched. And that's what I'm saying here. When the input and output impedances are different from the reference impedance, we require a definition of gain that accounts for these impedance mismatches. And this more useful definition of gain is the transducer power gain. And here is how we go about defining it. The bottom line is literally shown here on the bottom line. The transducer power gain is by definition the power delivered to the load divided by the available power. So we need to know what those two things are. Well, here's the power delivered to the load. So we have some Thevenin equivalent circuit for the source. We have the two-port of interest, which is given by its S parameters. And then we have some load Z sub L. And just given this much, you already know how to compute the power delivered to the load. We'll do it again here just so you know, just to refresh your memory. But the power delivered to the load is literally the power which gets dissipated in Z sub L. Now, the power available from the source is a concept you probably have not encountered before. Works like this. Here is some Thevenin equivalent circuit for the source. And what we do now is we terminate it into the conjugate of the Thevenin equivalent source impedance. So this is Z sub S, and this is Z sub S conjugate. And you already know from circuit theory that maximizes the power delivered. Any other value of the impedance will result in a smaller amount of power delivered to this thing here. So we call that maximum condition, when we have conjugate matching with the source, the available power. So transducer power gain is the ratio of the power that we deliver to a load through the two-port compared to the power that the same source can deliver to a conjugate match. And that's our definition. Okay, so available power. Let's just explain a little bit more about how this works. So once again, we have our Thevenin equivalent circuit for the source. And then we have a conjugate match to the source over here because we're going to compute available power. And here I'll define the current flowing through the load as I sub L, and the voltage across the load here as V sub L. And in that case, then, the available power is the real part of V sub L times I sub L conjugate, and you already know this. Note I'm using RMS units here, root mean square values. If I were using peak values, there would be a factor of 1/2 out front. I find this is something that often escapes the attention of undergraduate students. Maybe you didn't catch it when you saw it in a previous class. But once again, RMS units, no factor of 1/2 out front. Peak units would have a factor of 1/2 out front. Okay, so now I can make substitutions. So V sub L in this particular scenario, I can compute using a simple voltage divider, right? That's V sub S conjugate, that's this thing here, divided by the total impedance seen by the voltage source times the voltage source. So that's a simple voltage divider that I'm using to compute V sub L. And the current I sub L is simply the source voltage divided by the total impedance, right? And then I conjugate that. So now let me introduce some notation here. I'll say the real part of the source impedance is R sub S. The imaginary part of the source impedance is X sub S. And when you do the math, this is very simple to do. You should do it. I'm going to save a little space and time here and not do it. But if you have any problems with this, please seek help. I'm happy to show you the details. But once you do the math here, you very quickly find that the available power in this scenario is given by the magnitude of V sub S squared divided by 4 times R sub S, right, the real part of the source impedance. Now note again, if this were peak instead of RMS or some other representation of voltage, then that factor of 4 would potentially be something else. Like for example, for peak units, if V sub S is in peak voltage, that 4 would become an 8. Right? In general, in RF engineering, we use RMS units, but not always. So just be aware of that. This is where factors of 2, factors of square root of 2 show up as errors in calculations. Okay, the power delivered to the load. Well, we can do a very similar thing, except now I've got some Thevenin equivalent for not just the source, but the source followed by the two-port of interest. So I should use some different notation here, and to remind myself that I'm talking about a different input here, I'm calling them V sub TH for Thevenin and Z sub TH for Thevenin. So again, Thevenin equivalent for the source followed by the two-port. And we're interested in what's dissipated by the load, and we'll use the same notation here, I sub L for the current flowing through the load and V sub L for the voltage across the load. And the calculation works more or less the same. Again, the power is the real part of V sub L times I sub L conjugate. I can do the exact same calculation. I'll again define R sub L to be the real part of Z sub L and X sub L to be the imaginary part of Z sub L. And when I do the exact same algebra, I end up finding that P sub L, the power delivered to the load, is the magnitude of V sub TH, magnitude squared, times the ratio R sub L over magnitude Z Thevenin plus Z L magnitude squared. And that's the result here. Now, I'm going to note that this is not the only way to do this. In fact, this is rarely the way it's done. The reason is because this, in general, this Thevenin equivalent representation of the source followed by the two-port is kind of a pain to work out. If you know it already, great. You could do this and it'd be no problem. And for simple circuits, it's usually straightforward. But for most problems in RF engineering, this is more trouble than we're going to want to go through. And I'll show you an alternative way very soon in this very lecture. In fact, here it is. I can compute the transducer power gain if I know the source and load impedances and the S parameters of the two-port. Well, no surprise there because that's everything that defines the problem. So here's the expression. First, I'll tell you that I will not derive this expression. It's quite complicated, and really to do it properly requires a concept known as signal flow graphs. Not really a difficult idea, but it would take an additional lecture or two to get through that, and we don't really need that idea for the rest of what we're going to do coming up. However, if you're interested, please see any number of books. I would suggest Gonzalez, Microwave Transistor Amplifiers, 1997. In that version, it's section 2.6, although this concept shows up in a bunch of other places. If you're not interested in learning where this equation comes from, fine. I'll show you that it's correct by doing some examples, and we don't really need to know the details of how it came about. In any event, note that depends on the S parameters, S11, S21, S22, and S21. So all the S parameters are represented there. And then here's, again, another way of talking about the source impedance. Here's another way of talking about the load impedance. So everything that's relevant in the problem appears in this equation. First, we can do something to verify that this equation makes sense, right? I'll just say in general, whenever you encounter a complicated equation that you did not personally derive, or even if you did derive it and you want to make sure it's right, you should check it for some special cases. That's usually a simple thing to do. We have a readily available special case here, which is easy to compute, and that's the one in which the two-port is terminated into source and load impedances equal to the reference impedance. Because we know when that happens, in other words, when ZS equals ZL equals the reference impedance for which the S parameters are computed, then gamma sub S and gamma sub L are equal to 0. Right? And when gamma sub S and gamma sub L are equal to 0, this equation simplifies and becomes very simple. The whole equation just collapses down to this one factor here. And that makes perfect sense because that is in fact the intrinsic forward gain. That's what we expect to see. So saying this another way, the transducer power gain is in fact the intrinsic forward gain when the source and load impedances are equal to the reference impedance. In that special case, they give you the same answer. However, we'll note that in general, this condition will not be true. Not because, and frequently we don't even want it to be true. Like I said, there's principles of amplifier design, oscillator design, in which we do the design by making this untrue and exploiting the consequences. So in general, TPG and intrinsic forward gain, and I'm usually here talking about intrinsic forward gain, will be very, very different things. So don't think that this is a approximation or somehow generally true. That's not the case. It's only true in the special case where we've terminated the two-port in the way that gives us the intrinsic forward gain. So to try to clarify this, let's do an example. So here's the first example of two. The Thevenin equivalent model for the source is 1 volt RMS in series with a 50 ohm impedance. This could be anything. This could be in fact, it's a very general description, even though it looks very simple. This could be a signal generator, a perfectly adequate description of a RF signal generator that you might find on a lab bench. Our two-port will simply be a 50 ohm series connection, and we already know about how to analyze that. And our load will be a 50 ohm load. Again, even though this looks very simple, this could be a very broad class of things. It could be a receiver. Many radio receivers are designed to have 50 ohm inputs. That might be a sufficiently complete description of a receiver for this kind of analysis. So even though this looks like a simple problem, in fact, it's a pretty broadly applicable problem. So it's of interest. Okay, so here's what we want to do. We want to compute gamma sub s, we want to compute gamma sub L, because we'll need those eventually. We want to compute the available power and the power dissipated by the load, because those are the things that go into the definition of the transducer power gain. And then separately, we want to compute the transducer power gain using this new equation I just showed you, and thereby hopefully confirm that it's working properly. Okay, you have everything you need to do this problem. I suggest you go ahead and work it out, pause the video, and restart the video once you have some answers for this, and I'll show you how it works out. So pause the video now, and then restart, and I'll show you what the answers are. Okay, here we go, on to the answers. Oh, by the way, that's still example number 1. Okay, so here are the answers. Gamma sub s, well, that's just 0. It's 0 because Z sub s is 50 ohms, and presumably we're assuming the reference impedance is 50 ohms. All right, if that's the case, then gamma sub s is 0. Similarly, gamma sub L is 0, again, because Z sub L is 50 ohms, and 50 ohms is also the reference impedance, so these two values are 0. Now, they're not 0 because the actual reflection coefficients are 0. They're 0 only because we're using these as definitions, right? The reflection coefficients are alternative ways of talking about those impedances. They're not the actual reflection coefficients. So don't lose track of that idea. Okay, here's the available power. The available power is the magnitude V sub s squared divided by 4 R sub s. We worked that out in a previous slide. Make the substitutions, and we find out that we have 5 milliwatts of available power. Here's P sub L. Very simple to do this using simple circuit theory concepts. Here's a voltage divider to compute the power, the voltage across the load. Here's Ohm's law to figure out the current through the load. So very simple circuit theory concepts. We do all that, and we end up with the load. The power dissipated in the load is 2.22 milliwatts. The transducer power gain is the ratio of those two things. So 2.22 divided by 5, that's 0.444 repeating, which is minus 3.5 dB. So we would say the transducer power gain here is minus 3.5 dB. And we can compute that also using the complicated equation. But it gets simple real fast because gamma sub s and gamma sub L are 0. We worked those out before. So the whole thing collapses down to just magnitude S21 squared. That's magnitude of 2/3 squared. Again, we already know what the S parameters of this are from a previous lecture. And that gives us minus 3.5 dB. So here, everything kind of works. It works in a trivial way. In other words, we see that the two definitions of TPG give the same answer, but it's not really surprising because everything got simple here. But nevertheless, it's good to see. And we also have one example of a calculated transducer power gain, and they agree, so everything seems to be working. But to really kind of make sure this is working right, we should mess something up, make the impedances less well matched. So here's what I'm going to do. Example number 2, I'm going to increase the load impedance from 50 ohms to 100 ohms. So you know right away that gamma sub L is no longer going to be 0. Right? That's going to change. So everything else will be interesting to compute. But go ahead and do that now. Recompute the problem for this new situation where Z sub L is 100 ohms and see what you get. Go ahead and pause the video and restart it when you're ready to see the answers. Okay, here are the answers. First, gamma sub s is 0. That doesn't change because Z sub s didn't change. Gamma sub L becomes 1/3, right? Because Z sub L is 100, Z naught is 50, so gamma sub L is 1/3. P sub A doesn't change because P sub A depends only on the source. That didn't change, so it's still 5 milliwatts available power. P sub L changes because the load impedance changed. Now we have the load impedance, the load power, the power dissipated in the load is 2.5 milliwatts. So that changed from the previous problem. So we find that the transducer power gain is a ratio of 2.5 to 5. That's 1/2, which is also known as minus 3 dB. So the transducer power gain has changed. Previously it was minus 3.5. Now it's 3 dB. Now the moment of truth, we can use this more complicated equation. Gamma sub L is now non-zero. Here's the full S parameters for that 2-port, just for quick reference. And if you do the math correctly, you find that this is minus 3 dB. So sure enough, these two expressions, these two approaches give us the same result. So that should give you some increased confidence in this. Now, that's not a proof, but again, you should see that this is always the case. Now, you could keep going with this, right? You could change, for example, this to 100 ohms and repeat the problem. And now I'll point out that this is no longer equal to the intrinsic forward gain. The intrinsic forward gain is the magnitude of S21 squared. That's minus 3.5 dB in this problem. Now we get minus 3 dB. The gain, in some sense, has gone up. I promised you some foreshadowing about the concept of stability here, and let me just say a few words about this. So here's this expression we like for transducer power gain. You will note that there is a number of ways that the denominator in this expression could be 0. Now, if the denominator turns out to be 0, the TPG becomes infinite. It seems inconceivable that the output power could be finite, for example, when the input power is 0. But again, remember, TPG is not really a fundamental physical concept, it's a metric. One way to think about this is that no 2-port can have infinite gain, right? Something's going to break first. If you have an amplifier and you keep redesigning it so the gain goes up and up and up, eventually you hit some physical limit. It'll either be a rail and a power supply, or simply the fact that you can't deliver enough current, and something will conspire to prevent you from increasing the gain anymore. So in some sense, we'll never run into this situation. However, that's not the whole story. Because what can happen is that devices do have power supplies, and they do have things like negative feedback. So there are ways that with a finite amount of power, we can cause the power to want to escalate without limits. It will never get there, but it'll take off and do something undesirable. Now, this condition we call instability. For amplifiers, instability is usually bad. That's usually not what we want. For oscillators, that turns out to be usually the way they work. So it's a concept that we will have to address in some more detail, and we'll certainly do that in a lecture very soon. Now, stability of 2-ports, topic of an upcoming lecture, as I just said, and is a recurring topic of interest throughout the course. Understanding the stability of 2-ports is really key to both amplifier analysis and design and oscillator analysis and design. This concludes this lecture on transducer power gain.